All right, so now we know that two-level unitaries are universal. How are we going to do these in terms of single qubit operations and CNOT or two-qubit operations? So this is chapter 4.5.2, which is about single qubit and CNOTs being universal. And our strategy is going to be simply figure out how to do a two-level unitary in terms of single qubit operations and two-qubit operations, CNOTs. And we'll eventually have multi-controlled operations, but we know how to compile those back into CNOTs and single qubit operations. So again, I'm going to motivate this with an example. The textbook starts with a 3-qubit example. I think it's easier to see a 2-qubit example first. So let's consider this two-level unitary, A, B, 1, 1, C, D. So zeros elsewhere, explicitly 0, 0, 0, 0, 0. Like this, okay? So this will be a two-level unitary. And why is it two-level? Again, to emphasize, here it's a 4 by 4, so we can use our familiar Dirac notation. So U acting on 0, 0 will be A 0, 0 plus B 1, 1. U acting on 0, 1 will do nothing. It'll just give us 0, 1 back. U acting on 1, 0, again, will do nothing, just give us 1, 0 back. And then U acting on 1, 1 will be C 0, 0 plus D 1, 1. Okay? So it's the way to think about it, it's a single qubit unitary, A, B, C, D, embedded in a larger unitary. And we call that two-level. Let's denote this 2 by 2 submatrix, A, B, C, D, as U tilde. And we know that this is going to be a unitary matrix. So this is unitary. Again, that's just by definition of sort of what we mean by a two-level matrix. Now, the key idea is that this unitary almost looks like a controlled operation. It's not exactly going to be a controlled operation, but let's remind ourselves what controlled operations are. We're going to think about a controlled U tilde operation and see if that looks anything like the unitary that we want to do. Okay? So let's consider, as an exercise, evaluating controlled U tilde, meaning control on the first qubit, target on the second. So this will be 0, 0 tensor identity plus 1, 1 tensor U tilde. And then let's also evaluate the control, but with the control and target flipped. So I'll indicate that with a 1, 0. So here, I'm going to be controlling on the second qubit. So I'll put identity tensor 0, 0 plus U tilde tensor 1, 1. All right? So your first exercise is to evaluate which each of these controlled U tildes are and see if it looks anything like the two-level unitary U that we want to implement. All right, so this controlled U tilde we've seen before. Just to be explicit in a circuit, I mean, if the top qubit is indexed as the first one, we're doing this operation, controlled U tilde. And in the bottom one in the circuit, I'm flipping the control and the target. So that would be target on the top qubit, controlled U tilde. The first one we've seen examples of how to do. It's always identity in the upper left block, U tilde in the lower right block. So that as a 4 by 4 matrix would be 1, 1, there's the identity, and then we have U tilde, A, B, C, D. Okay? So this kind of looks like this U, It's not super similar, so it might take some thinking. Let's try to evaluate this one and see if it's any closer. So when you work this out, maybe I'll write one step. So again, identity matrix, tensor, this projector is 1 in the top left, 0 everywhere else, and then plus we have A, B, C, D, tensor, the projector onto the 1 state, 1 in the lower right, 0s everywhere else, right? By the way, you should be able to evaluate these. I think I mentioned it before, but the notation is good. It tells you where the 1 goes. So the 1 is in the 0, 0 component. So go down 0, go over 0. That's where the 1 is. Here, go down 1 over 1. That's where the 1 is. Okay. So the same is true for the other combination, 0, 1, and 1, 0. So outer products are easy to evaluate. You just have to realize the binary notation tells you where to put the 1. Everywhere else is a 0. All right, so when you work this out, I'll just write the final step in the interest of space. You will get the following matrix. You'll get a 1 in the upper left, A, 0, B, 0, 1, 0, and C, 0, D. Okay? And of course, zeros elsewhere. This one kind of looks like the U that we want to do, the 2-level unitary, but not exactly. I'm going to claim that we can sort of go from this U to this controlled U by swapping certain rows and certain columns in this 2-level matrix. So let me show you what I mean by that. Let's start with this U, and what I'm going to do is I'm going to swap the first 2 columns. So let me be very explicit with the indexing so you understand what's going on. The columns right now are indexed in the following order: 0, 0, 0, 1, 1, 0, and 1, 1. And the rows are indexed in the same order: 0, 0, 0, 1, 1, 0, 1, 1. Right? If we just write down a matrix in the standard computational basis, this is the ordering that we mean. Okay? So the first thing I want to do is I want to swap column 0, 0 with column 0, 1. Okay? So that means I'm going to take this column, put it here, and this column, and put it here. So the matrix that we get when we do that will look like the following. I'll get 0, 1, 0, 0. That's the second column of this matrix, becoming the first column after I swap, right? And then I'm going to take the first column and put that as the second one. So that's A, 0, 0, B. The last 2 didn't change, so 0, 0, 1, 0, C, 0, 0, D. Okay? So the ordering now is that we've swapped the first 2 columns. So this is now what the unitary matrix does to the 0, 1 states. This is what the unitary matrix does to the 0, 0 state. And the last 2 didn't change. And now we have the row ordering hasn't changed yet. So 0, 0, 0, 1, 1, 0, 1, 1. Okay? So the next thing I'm going to do, maybe you're looking at this. This looks pretty close to this controlled U tilde that we worked out what it was, right? If only I was able to put the first row as the second one, then actually we would have exactly this unitary. Does everyone agree? So let's do that. Now let's swap the first 2 rows. So swap row 0, 0 with row 0, 1. And when you do this, you'll see that you get exactly this controlled U tilde with the control on the second qubit. So that comes out to be the matrix 1. Let's start from here just to check. So I'm going to swap these first 2 rows. So the first row will become 1, 0, 0, 0. So that's 1, 0, 0, 0. Second row, 0A, 0C. Last 2 rows don't change: 0, 0, 1, 0, 0B, 0D. And you see exactly that I now have this controlled U tilde operation. 1 in the upper left, A0C, 010, B0D. Okay. So that's nice. Now, if I were able to do as a unitary matrix this operation, swapping the first 2 columns and swapping the first 2 rows, then I would be able to implement this controlled U. That's a controlled operation we know how to do in terms of CNOTs and single qubit gates. Then I would be able to do this 2-level unitary that we care about in terms of single qubit operations and CNOT gates. Okay? The only question we have left is how to do the swapping of the rows and the swapping of the columns. So we need to ask ourselves the following question. What circuit operation, or what gate, do we know that does the following map? So we want to map 0, 0 to 0, 1 and 0, 1 to 0, 0. Right? So this is a sort of explicit way of saying that we're exchanging the two. Right? 0, 0 becomes 0, 1. 0, 1 becomes 0, 0. That's exactly what we were doing by swapping. Okay? Could anyone think what quantum operation, what gate do we know that would implement this transformation? Explicitly, we want the other ones to stay the same. So 1, 0 would not change, right? We weren't changing 1, 0. And then 1, 1 also would not change. You might have to think for a minute, but this works out to be the anti-controlled NOT. Okay? If 0, flip the second bit. If 0, flip the second bit, that'll give me 0, 1. If 0, flip the second bit, that'll give me 0, 0. And then the other two won't change. So explicitly, I don't want 1, 0 to change. 1, 0 shouldn't change, and then 1, 1 also shouldn't change. The anti-controlled NOT has us covered for this too, right? Because we're saying if 0. So in this case, in these cases, the first two bits are 1, so we don't make any change to the state. So this is exactly, the answer to this is the anti-controlled NOT operation. Okay? Anti-controlled NOT with the control on the first qubit, right? We're controlling on the first bit in this. So this is a matrix, just to remind you. Anti-controlled NOT would be if 0, do x. If 1, do nothing, do identity. Okay? If you want to work this out, I'll note to you as a matrix what this would look like. X in the upper left block, 0, 1, 1, 0. Identity in the lower right block, zeros elsewhere. That will be useful if you want to check this construction. But what we've just showed is that a circuit for this two-level unitary, and we know that two-level unitaries are universal, is exactly anti-controlled NOT, this controlled U, and then anti-controlled NOT on the right again. And so I'll write down the circuit, and then I'll motivate why we need to do it on both sides. So this U that we care about, this two-level U, can be implemented in the following circuit. Anti-controlled NOT, controlled U tilde, and then another anti-controlled NOT, like this. Anti-controlled NOT, we know how to do in terms of CNOT, right? It's just a CNOT with an X on either side of the control. And then we also had a way to do a controlled any single qubit operation in terms of CNOTs and single qubit operations. Do you remember this? We had it from, well, before spring break. But we could look back and remind ourselves how to do this. Therefore, and then same thing for the second anti-controlled NOT. Therefore, we're able to do this two-level unitary in terms of single qubit operations in CNOT. And the same will be true for any two-level unitary. So that will be the next example that we'll do. Just to emphasize, why do I need to do this anti-controlled on the left and the right? Who could argue why that is the case? Remember, we needed to do two swaps. We first needed to swap columns, and then we needed to swap rows. This one will be the column swap. This one will be the row swap. Okay? You could argue why that is in terms of the basis states. You could also do this sort of 4x4 multiplication explicitly and see what's happening there. When you multiply from the right on this unitary matrix, that will be changing the rows. When you multiply from the left, that will be changing the columns. It might be vice versa. It's easy to mix up. But one does the columns, one does the rows. So that's why we need to do it on either side. And then we have the controlled U tilde in the middle. This U tilde is a unitary matrix, so we're allowed to control that and do that controlled operation.